Bueno, creo que ya podemos comenzar. Entonces, vamos a dar inicio a este último sábado de conferencias en el marco de la cuarta escuela de superconductividad. El día de hoy tenemos la plática que nos dará el doctor Omar de la Peña Siman, quien es profesor investigador del Instituto de Física Luis Rivera Terrazas de la Benemérita Universidad Autónoma de Puebla. Damos la bienvenida al doctor Omar de la Peña, pues, y le agradecemos su participación en esta cuarta escuela de superconductividad, dedicada principalmente a mover los estudios en este campo entre los estudiantes que están en los diferentes posgrados de áreas afines a física. Bien, Omar, pues te damos la palabra. Me entiendo que hay participantes extranjeros y en principio puedes incluir algunas palabras para ellos. Ahorita yo voy a hablar un poquito en inglés para que ellos también tengan entendido eso, ¿sí? So, for our invited foreign scientists which are participating in this conference, in the fourth Saturday of the fourth School of Superconductivity, I would like to mention that the talk today is given by Dr. Omar de la Peña Siman, who is a scientist working at the Institute of Physics in the Autonomous University of Puebla. So the talk will be in Spanish, but perhaps Dr. Omar de la Peña will include some comments in English during the talk, as I understood. Yes, Omar? And then I give you this presentation to Dr. Omar de la Peña. Thank you for your participation, Omar. So you can.
Gracias, Felipe, gracias por la introducción. Ahora voy a switchear al inglés, como dijo Felipe, en atención a nuestros invitados extranjeros. Y bueno, so thank you for your assistance to this last session of the School of Superconductivity, the fourth School of Superconductivity. I would like first of all to thanks to the organizers for allow me to talk a little bit about some of my research topics nowadays. Many of the slides are in English. It was a fortunate situation. However, if you have some question, please don't hesitate. Ask me during. If it's a very short comment or doubt, feel free to interrupt me. Or if it's more an elaborated question, we could leave it at the end of the presentation. Also, you want to talk to ask me in Spanish, there is no problem, and I will try to translate in English, or foreign invited participants could understand what we are discussing about. So the title of my talk is Superconductivity and Electron-Phonon Coupling in Light actinides, and this is a not very new topic that I've been studied along the last 4 years, but the new part here is we are using these systems and these properties to tracing down a high-order interaction, particular strong correlation interaction in electrons. So as Felipe said, I'm working in the Institute of Physics, Luis Rivera Terrazas, in UAP in Puebla. So as a brief, before the talking, I would like to acknowledge my collaborators in the university and my foreign collaborators in foreign countries, sorry. Two former students, master students, Paola González Castelazo and Romeo de Cos Martinez. Some of the results I'm presenting were part of their master thesis. And another collaborators from the KIT in Germany is Dr. Rolf Hyde and Dr. Klaus Pitabonen. It's a very long-term collaboration that I've been established with them since I was a PhD student many years ago. And the former name of the institute was IFP, Institute of Solid State Physics. But nowadays they merge with and create a larger institute that is Institute for Quantum Materials and Technologies at KIT. So obviously all this work was being financed, has been funded by CONACYT and our internal Office of Research and Graduate Studies, that is BEP in WAP. So as a brief, this is the outline of my talk. We will talk a little bit about the superconductivity, what it is, how it's working, a particular model to explain superconductivity in one specific family of superconductors, that is the electron-phonon coupling. And then I will focus on the materials that I'm interested on, the light actinides, what are they and what are used for. Now the topic of our school, that is superconductivity in actinides, how important or interesting could be. And then this electron correlation, how important could be for these materials and specifically for the superconducting properties, some results that we have obtained, and some current and future work about this particular topic. So starting with the superconductivity phenomena, all these phenomena started with a very simple, a very interesting question. Now, at the beginning of the 19th century, was the hot topic, and now on those days, was to try to understand the resistivity at very low temperatures. There were a lot of different models and ideas and discussions what's going on with the resistivity of metals at very low temperatures. And remember that at that time, the temperature that you could reach with the current, at that time, the current technology was not so low as nowadays. And so this was a very interesting topic in that time. And was not until this day, in this year, in 1908, that Camerlion's in his lab construct this equipment that was used to liquefy helium. And with that instrument, they were able to reach temperatures below close to one Kelvin. And in that time was a huge hit in the science, in the physics science. One experiment or one material that they used to test and verify and check their equipment was mercury, actually. So they perform measurements. This is the original plot of the original paper. They are plotting temperature versus resistance versus temperature. So the ideas at that time that was going on with resistance or resistivity at low temperatures was, one model was going linearly until absolute zero. Another model was increasing suddenly. And another model was dropping constantly until zero. That were the current ideas. And none of these ideas could think about or could imagine the actual behavior of some of the materials, for example, mercury, that at some point in some temperature, the resistance dropped dramatically, practically to zero. Okay, and after this observation of this particular properties, Professor Cameleons and his team starting for several months to try to reproduce the results because they thought that was an error or a mismeasurement. But in every test that they perform, they get exactly the same results. So at the end, after several months of trying to testing this equipment, because the prototype was the first one in his kind, they were absolutely sure about the results. And because of this technological development, Cameleons got the Nobel Prize in the 1913. And in the announcement was for his investigation of the properties of matter at low temperatures, which led inter alia to the production of liquid helium. So he got the Nobel Prize because this very important advance in basic science. However, when Cameleons gave his talk of acceptance of the Nobel Prize, he stamped the name of this new phenomena that he discovered thanks to this to the achievement of liquefying helium. And his talk, he mentioned that, as has been said, the resistance disappeared. The disappearance didn't take place gradually, but abruptly. Thus, the mercury at 4.2 Kelvin has entered a new state, which, owing to this particular electrical properties, can be called the state of superconductivity. And at this moment, and this year, the superconductivity was born as a new phenomena, as a new state of matter. Okay, and basically, was experiment as you see, was experimental observation. Wasn't any kind of model of description of explanation what's going on in material at very low temperatures. Was a very excitement about this. The people was very excited about the scientific community about this breaking in the science. A new state of matter was discovered, and the imagination started to fly about having cables that transport electrical currents without any loss of energy, because using just this kind of materials could help a lot in this technology. Well, at the beginning it was only a dream. Nowadays it's a reality in many cities and many developments, technological developments. So this is how superconductivity was born. Obviously, from the beginning of the 19th century and nowadays, has been a lot of work trying to discover new material, new superconducting materials, try to understand these materials, and just to have a feeling how active and intense is this area. I show you this plot. This is a critical temperature versus the year of discovery of the different materials. So there are different families. This is the standard superconducting materials, as we will discuss a little bit further. These are the high TC materials. Probably you have heard a lot of them along the different talks in the school. There's the carbon-based materials, the heavy fermion materials, these green stars. Okay, the nanotubes, obviously the nanotubes are everywhere. So why not also in superconductivity? Well, they are here. And recently, very recently, 15 years ago, started a new family was discovered, and this was a breakthrough in the theory of superconductivity because it was in principle two different opposite interactions that fight each other for the supremacy in the material, that is magnetism and superconductivity. They play together to get a new family of superconductors. That is the pnictides. Basically, there are materials with iron or a specific magnetic material, and in this case is iron, with the family of arsenides. And these are extremely interesting and very similar to the high TCs in the physics and the behavior of the measurements that they are getting. And now, 5 years ago, was discovered, after a long time of research and basically theoretical research, in systems based in hydrogen, was discovered superconductivity, but at very extremely high pressures. Because this system, H2S, in atmospheric pressure is gas, it's a gas phase, so you have to compress a lot. First of all, to solidify, and after that, to metallize. You have to have a metal in order to get a superconductor. So you have to put a lot of pressure in the material. It's around 155 gigapascals. Just to get an idea, this pressure you could get in a pictorial way. If you put one African adult elephant in top of each other, three elephants in the area of a pin. Okay, so this is the amount of pressure that you have to apply to this material just to get the superconductor. However, as you can see, this is one of the highest temperatures that you could get for superconductor materials. Nowadays has been discovered in the last couple of years systems by basing in hydrogen that could reach close to 290 Kelvin, very, very close to ambient room temperature. Let me moment one. I think there is a question. Let me check. There is a comment. No. Okay, let's go back. So, and in this part, it's just to have a feeling in the lab how low you could go to the temperature. For the first one, you have to liquefy helium to reach this temperature. Now, for the typical materials used in the industry, at least at the beginning of the 2000, you have to liquefy hydrogen. For the high TCs and the pnictides, you have to liquefy nitrogen. And for the last members of the newest members of the high TCs family, you have to liquefy this gas. But for the hydrogen family, basically with a standard lab refrigerator, you could get to these temperatures. So it's a very, very active area, the superconductivity from the basic point of view, basic research. But also for the active research, I mean for technological advance, probably this already was talked in different sessions the last couple of weeks. But this is a very nice example I like very much to mention in my talks in superconductivity, because it's an actual application to the superconductivity to a real problem. Basically, it's the transmission of electrical power in a city when you don't have enough space to construct substations to give additional power to their grid in order not to lose too much power in the electricity. So this prototype was started to construct in 2015 in Essen in Germany, and they construct basically two substation here in Delbrugge, here in Hercules, and they are connected by a facility that is special because all the equipment in order to get these cables are cables constructed by superconducting materials, basically MgV2, and all the machinery and all the engineering that you need in order to get lower temperatures, special bombings, and so on and so forth, are established here in this middle point. So the length of this facility between the middle substation and the two different substations, the Delbrugge and Hercules, is about 2 kilometers, and this is about 3 or 4 kilometers. And this was just a prototype, a very small one inside of the city, just to show how convenient from the economical point of view and scientific point of view could be used as superconducting cables instead of standard copper cables for the transmission of electricity. It was very successful. I'm not very close to the project. How is the reach of these ideas, and how far has been taken, but was very, very successful at the very beginning. Now, how about the description from the theory about the phenomenon of superconductivity? Because we already saw how how it was discovered, and what are the applications and what the materials are. But the theoretical description by fundamental science and fundamental arguments was not given after almost 50 years, not 15, 50 years of his discovery, okay? And one of the current models widely accepted for one of the specific families of the superconductors is electron-phonon coupling, okay? How the people reach this or get this idea, this brilliant idea to explain superconductivity in the standard superconductors? Well, they plot along many analysis and discussions about these materials. They plot the critical temperature of the mercury for different isotopic samples. I mean, different masses in the nucleus, okay? As a function of the root of the mass of the isotope, okay? And they got almost a linear behavior between temperature and the inverse of the root of the mass. And this was a kind of very interesting and important analysis, because this is a very nice description of the one quantity, fundamental quantity, or a measurement in a fundamental quantity of the material. And the people that came to the description, the group of people that came to the description, theoretical description of superconductivity, was very shocking by these measurements, because it's extremely well related to another quantity that has the same fundamental relationship with this quantity, 1 over the root of the mass of the material, and that's the frequency. Remember your harmonic oscillator? Basically, the frequency of the harmonic oscillator has also this fundamental dependence. So the people, these three very intelligent and hardworking people, Joe Bardeen, Cooper, and Schiffer, came to the idea to propose a model which relates the vibrational properties, the lattice dynamical properties of the material, with his superconducting properties. And that's how, with the observation of this kind of plots, this is how the idea of the conjunction of the electronic properties and the vibrational properties came together. And they called the electron-phonon interaction. And for that brilliant idea, these three people, these two persons, get the Nobel Prize in the 72 for the jointly development theory of superconductivity, usually called BCS theory. And this is because the first letter of his last name of these three guys. And just for some of you that didn't know, Joe Bardeen is one of the few persons that have won two Nobel Prizes, but in 2 different areas. He won a Nobel Prize in chemistry, and also he won the Nobel Prize in physics. For physics was the BCS theory. So he's extremely brilliant guy. And what is exactly how work, or how could we explain the electron-phonon interaction for a superconductor, and how this could give place to the superconductivity? Well, the model works more or less like that. Imagine that this is the superconducting material. These blue dots, these blue spheres are the ions, and these red spheres are the electrons. Okay? So, as you probably know, the material, even that it is a very low temperature, is continually vibrating. It's always vibrating by his quantum nature. So this material is vibrating in different modes, in different patterns, and when the specific conditions put together, in principle, when you have this particular vibration of the network of ions, and in that particular moment where these ions are getting closer, one electron is passing through. So these ions, okay, get more attracted by the electron. So the distortion is even bigger. And this distortion encapsulates in some sense or protects or screens the charge of the electron and creates a net positive charge, very localized region of positive charge in the network. So another electron that is traveling close by, he didn't see any longer the negative charge of the original electron. What he sees is the positive net, very localized charge created by this distortion and by the attraction of the first electron. So this second electron is getting attracted by this net positive charge. And since these electrons are traveling, the first electron gets coupled with this distortion, and this first electron travels with this distortion along the network. And because this electron travels with this distortion, and this distortion generates a net positive, very localized charge, the second electron is traveled with it. Okay, so this is how it formed this coupling. The two electrons are coupled together, traveling together along the network by a distortion, of the lattice. Okay, and more or less we understand that they are coupled together, they are traveling together along the lattice. But what had to do this with the superconductivity? Well, this is the brilliant idea. These two electrons are fermions, but because they are coupling together by a phonon, this is called a phonon, so they form a new particle, and this particle is called a Cooper pair, and as a particle, they behave like a boson. You have one fermion with one spin, one half, and another fermion with minus half, so you have a boson with a spin equal to 0. And because you have a boson, all your bosons could live in the same state, basically without any kind of loss of energy between each other. So that's why the superconductivity could take place in systems like that. Now, how big or how small are these distance of coupling between electrons? Just to have an idea, the particular space in a lattice, in a solid, that is superconductor, is around 0.2 or 0.4 nanometers. So the distance between two electrons that form a copper plate is around 100 nanometers. So it's a long-range interaction in terms of, in comparison with the standard size of the lattice. Okay, so it's a very, very delicate conjunction of conditions that take place the superconductivity. And that's why you need to be at very low temperatures in some systems, because you have to have these particular phonon modes very, they have to present at particular conditions the vibrational properties, I mean the frequencies and the vibrational phonon modes, with how many electrons could be available to couple to this particular movement. So this is the phonon, electron-phonon coupling mechanism that describes many of the properties of a family of superconductors that are called the standard or the BCS superconductors. Okay, this is the phenomena, and this mechanism is not the same. The mechanism that explains the formation of Cooper pairs is not the same for each family of the superconductors. However, all the superconductors form a Cooper pair. The difference between the families are basically which mechanism generates the Cooper pair. Okay, so this is the only slide that I will show some equations. Don't worry, and just to have an idea, a feeling how important are the different quantities that we are going to discuss along the talk. So this is the spectral. We are using the most modern theory to describe as a standard superconductor, that is Elias-Verr formalism, and the most complete nowadays. And then the kernel of this theory is the Elias-Verr spectral function, basically given by this equation, where is introduced the density of states at the Fermi level, is the line width, is basically the inverse of the lifetime of the signals, the frequencies of the phonons, and you are using just the normal phonon modes. Okay. So how you could calculate these quantities? Well, first of all, you have to characterize with a single number how strong or how weak is the coupling in your superconductor. And that you are doing by the electron phonon coupling constant. That is the lambda value. And basically it's a weighted integral of the Elliott spectral function in frequencies. Okay? And this integral you could also present as a summation in the line widths, in the frequencies square, and the density of states at the Fermi level. However, how you calculate the line widths? Line widths are calculated basically with the matrix elements of the interaction itself, the electron phonon interactions, by this joint density of states. So basically this is a kind of density of state square. So if you put together this information here, you are getting that as a very naive but interesting and very helpful approach, that the electron phonon coupling constant is linearly proportional to the density of states, because this is a density of states square. With this down, then you get a linear relationship, proportional relationship between lambda and density of states. So if you are looking for a good possible material, superconducting material, you have to look at quite high value of density of states at the Fermi level in the electronic properties. And what about the frequencies? We are getting an inverse square relationship between lambda and frequencies. Well, it's not true at a first sight, because the line widths have these frequencies here. So you put this information here, so these frequencies goes out with this square, and then you are getting again a fierce and a zero approximation, a zero approach. The lambda is inversely proportional to the frequencies. So this is the main idea. How you are so this is the main idea that I want that you keep in mind. How lambda varies as a function of electronic properties and frequencies. Is linearly proportional to the electronic properties, the density of states at Fermi level, and inversely proportional to the frequencies. So if the frequencies goes down, it's good for superconductivity, and if the density of states goes up, it's good for superconductivity. And depends linearly in lambda in the matrix elements. How you calculate the matrix elements? With these integrals, where you get a perturbation of the potential, because the electron phonon coupling between different, and this perturbation of the potential due to the phonons couples different electrons that could be coupled basically by this phonon. And this is the pattern of vibration of the particular phonon. So here is where you get the core or the kernel of the interaction, the integral that is generated by the perturbation in the potential due to the movement of the atoms that allows to couple one electron to another by a phonon. Okay, so the main idea, how lambda is affected by the density of states and frequencies. Density of states linearly and frequencies inverse in an inverse way. So we are going to analyze these effects in the electron phonon coupling. So now we are going to discuss the material, how important these materials are. The actiness. Who are the actiness? The actiness, basically, you look, your periodic table is the last line in the last row in your periodic table, at the very bottom. Okay, and these are classified more or less arbitrarily into different families. The light actinides is the first 6 elements of the family, goes from actinide until plutonium. Okay, and why they are classified in that way? Because the 5 F electrons that characterize this family has an itinerant behavior. That means that they are traveling, these 5 F electrons are traveling along the crystal. And the other part of the family are the heavy actinides that start also with plutonium and ends in the last column of the row. Okay, and what's the characterized situation or the important characteristic of the heavy actinides? That the 5 F electrons are very localized in energy and also in the space. They don't like to be traveling along all the solid. They like to be very well localized in strong bondings in your crystal. Okay, so this is more or less the classification of the actinides. So we are interested in the light actinides where the 5F electrons are itinerant. That means they are freely to travel along the solid and participate actively also in the bonding. Now, one very important point of the actinides, in general, all of them, is that they are radioactive. As you could see, here is uranium, here is plutonium. So what's your first idea when you heard that some materials is radioactive? Well, my generation thought about that. Okay. The newest generation thought about that, but not in restrictive of how, when did you born or what's your background and so on and so forth. Everyone, when think about radioactive, think about that. Okay. So it's a synonymous of bad and war and destruction and so on and so forth. And unfortunately, because all these nuclear accidents have been along the history, is this idea, in some sense, is right. However, there is light at the end of the tunnel, but actually the radioactive elements have been studied a lot along these last years. For example, thorium, the second element in the actinides family, is a very good candidate to replace as a fuel for nuclear reactors, replacing uranium for different conditions and different properties that thorium has. The more important one is that you can't have a chain reaction that could give an accident in a nuclear reactor with thorium, because thorium has to have a kick out of energy in order to start the chain reaction. And if you suddenly stop that induction of energy, the reactor stops immediately. So it's very, very safe using thorium instead of uranium. So this is the path, very slowly path, but the path to new reactors, more safer and more efficient than the uses for uranium. And another important advantage of thorium is that his disposal cannot be used to create dirty bombs, as in the case of uranium. Okay. So these are the actinides. How about his superconducting properties? Because, well, we're talking about superconductivity, right? So how we started in the group in WAB and in Germany about wanted to study the superconductivity in actinides was because of this paper. This paper was published in the ADA by Scriver in the PRB. This is a theoretical paper, and they try to calculate the electron-phonon coupling parameter for different materials, and in particular these materials that I interested in, the actinides. And you could say, okay, what's important about this plot? Well, the thing that I was astonished about this paper was this value, the actinide. According to the calculation of Scriver, the actinide has this value of electron of lambda that was higher than the highest one measured for a single element in the periodic table, that is lead. Lead has a 1.55 value of lambda for a single element, and lead has the record. And actinide, according to the Scriber calculation, had a higher value than lead. Just to give you an idea, how you could classify the value of lambda, what is big, what is small, and so on and so forth. Before the hydrogen-based superconducting materials was established that value of lambda above 1 was high. Below or close to 0.5 was, below 1 was medium, and below 0.5 was very small, okay? So having something close or larger than 1 was spectacular, because that gives you the possibility to have a very good superconductor, in the sense to have a very large TC. So how Scriber made this calculation in the 88s, remember, more like close to 30 years ago? Well, they used the experimental TC measured for thorium, protactinium, and uranium, and with a kind of empirical procedure, they could get a sense of the value of how lambda could be for these materials. You could see the values of the TCs are very, very small, 1.4 for thorium, Kelvin, 0.43 for protactinium, and 0.45 for uranium. And if you compress the uranium to 1 gigapascal, you could get 2.1. So they are very extreme values. But because of the properties of these materials, they are quite interesting in the physics, all the interaction they are playing around. So it's very interesting to study, despite the value of this, the value of the TC. So what's calculated? What means this dot and these triangles? The dot means was an empirical, the triangles means that was an empirical calculation. That means they just invert the equation to calculate TC, and using a standard value of mu star, that is the kind of repulsion that the electron feels when you have this construction of Cooper pairs, they could deduce the value of lambda. Okay, and this theta is basically the measure, this is the divide temperature, is the measure of how strong the frequency, the lattice dynamical properties are affecting the critical temperature. So with these two models, using a standard value of 0.13 for mu star, this kind of repulsion that electrons feels, and this scaling of the mu star, they could get these values. Obviously for actinium, since there is any kind of experimental measure of TC, they couldn't use this empirical scheme. So they use a more theoretical one. That is, at that days, the more modern theory to calculate the superconducting property was the Gaspari-Jorphy theory, using the Jorphy parameter. Basically, this theory gives all the importance to the superconducting properties to the electronic structure by the Jorphy parameter, given the density of the states. And the part of the frequencies are just an scaling of the divide temperature. So it's in a second plane, so to speak, of importance, the frequencies in this model. And with this model was also calculated the TC, the lambda for the different elements in the family. So the Scriber and co-workers were very happy because they got more or less the same behavior with the two models. However, actinide gives extremely, extremely high value. So I was very curious about this value. So we started to calculate with all this machinery that we already have, almost more than 30 years after this original paper, and we get these results using scalar relativistic methods, first principle methods, or including the spin-orbit coupling interaction. Because these elements are quite heavy, a spin-orbit coupling interaction is mandatory in this calculation. Well, we did it for the two approximations. It was published in 4 years ago. And what we get was I was a little bit disappointed. I couldn't get a very high value actinide, but at least was correct in the sense of the physics that was observed for actinide. Wasn't any kind of sign that the actinide was very high in TC at that moment. But I was very disappointed because I couldn't reach a high value as predicted by Scriber. However, our results gave a lot of light for these kind of materials and these kind of properties. And what about TC? Because this is a more interesting quantity for this kind of materials. Well, here is the evolution of TC as a function of the parameter, this Coulomb parameter mu star in the TC theory. Since all the quantities, all the quantities that you need to calculate the superconducting properties, you could get from first principle calculation, except the mu star. The mu star you have to feed in some sense. Okay, so the standard way is that you observe the experimental value of TC and starting to vary the value of mu star in your calculations of TC, and when you are close to the experiment, then you fix the value of mu star. And then from that, you can start to make some prediction or discussion about variation of different parameters, okay? So this plot shows that kind of tracing down, no? The TC as a function of mu star. And this orange region shows the standard values used in the literature for metals that are, so to speak, recommended to use for mu star. And this recommendation came from a lot of work that are using this theory to study superconductors. So it's between 0.1 and 0.13. So I was very disappointed with this plot at that time with my students, because the most complete calculation was closer to the experiment. This is the scalar relativistic calculation. The incomplete calculation was closer to the experiment for thorium, and the complete one was very far away from the standard values of mu star and the experimental value of TC. This cross, as you could see. I will be happy if this cross will happen in this region, okay? And the same and this was very low actually. That means that my value of mu lambda was very low. But I calculate everything right. I include all the interaction, all the details, and even in that case, I get a very low value of lambda. That was, as you could see here, less than 0.5. And for Protactinium was the opposite. I get a very high value for both approximations of lambda, because I had to include a mu star very high in order to kill that high lambda. And I got a little bit higher than 0.5 in order to get experimental TC that was below 0.5 Kelvin. So I was very disappointed and stressful, because what's going on, I mean, it is not a clear tendency. In one case, I get a very low lambda, and another case, a very high lambda. So what's going on? That idea was chasing me a couple of years. I was thinking, and after I found a couple of papers that give me the answer that could be missing in my calculation. And that's is related to the electronic correlation. What is the electronic correlation? Basically, the LDA plus U or DFT plus U model. Basically, when you have this correlation between electrons, you have your Hamiltonian, and you have this interaction that is basically the basic interaction that you have in the electronic system, the pair creation annihilation operator. And also you have the interaction between the electronic charge density. So the U basically. This U parameter modulates the interaction of your electronic cloud, and this modulates the standard interaction that are present in your basic Hamiltonian. When you transform this information to a DFT calculation, basically to Hamiltonian, to your DFT consham Hamiltonian, is represent this part, because this is already included in the Coulomb interaction, and actually these high order interaction are very small, okay, in your DFT standard calculation in your model. And that means that this parameter T is much larger than the U parameter that modulates this interaction. So this is basically the behavior of your electrons, and all of them are more or less centered at the Fermi level. It's a picture of the electronic density of states. However, what's going on when the U is equal or even larger than your T parameter? Well, your system wants to behave like that. It's no longer located in the center of your density of states at the Fermi level, is split into different regions. And that cannot be achieved by a standard DFT calculation. You have to include this interaction, not only the Coulomb interaction in your potential, in your Hartree potential, but an additional interaction in your Hamiltonian. And how do you do that? You have to create a new functional. Basically, it's your DFT functional plus this U functional. And you have to subtract the double counting of the electrons, because the electrons that you are trying to include here are already taken into account here. So you have to take it out. And you take it out by the J interaction. This J interaction is related with exchange of two electrons. So this is very, is reminding of the Hartree-Fock theory when you are dealing with Coulomb interactions, higher order interactions, and exchange interaction. Okay? So you are taking into account explicitly with this operator and the AU operator. So at the end, your functional, your DLL, DFT plus U functional have this form, including this part, the DFT part, and the U part. So basically you have a relationship between the parameters, the Coulomb parameter and the exchange parameter, with these summations in the different levels of the electrons. So with this theory, basic theory, you are able, playing around with this parameter, this U minus J is the effective U that is used in the literature. You could get basically the correct behavior for different materials where this interaction is more important or is equally important than the standard interaction of your electrons. So that's how you could include these high order interactions of the electrons. And what about your materials, the actinides? Well, in the 2004, a Russian paper was discussing how important could be these high order interactions, the U, in the actinides, specifically in thorium. And they were studying thorium, the electronic properties of thorium, as a function of pressure. So in order to get a proper description of the 5F elements, despite that they are itinerants, in certain conditions, they will need these high order correlations in order to describe properly the electronic properties of the material. So by a first principle calculation, Lukoyanov and co-workers reached these values, these parameters U and J, in order to get a proper description of the 5F electrons in the electronic properties of thorium. That gives you, remember this is a minus, U minus J, is the U effective that you have to include in your calculation in order to take into account these interactions. This value is quite low actually. Normal values or high values are 4 EV, maybe 5 EV for uranium or uranium compounds, uranium oxide, for example. So it's a very low, but how important could be? Another sign that could be very important, these correlations in materials, in actinides, is this paper from Dane Morgan in the 2013 about uranium, how it could be affected his structural or cohesive energy properties by including this Hobart parameter in the calculation, in the first principle calculation. And they reach a value by first principle that they need in order to reproduce experimental observations of 1.87. So for actinide, for thorium, 1.89, and for uranium, 1.87. And remember, in the periodic table, you have thorium, after that protactinium, and after that uranium. So thorium has 1.89, uranium, that is the third, 1.87. So I played with the numbers, and by a linear relationship, protactinium should have 1.88. So I get those numbers and put all the machinery, the DFT machinery, to get results and see how important could be these values for the properties I'm interested in. So first of all, the structural properties, I include this value for calculate the equilibrium volume for thorium and protactinium. This is the standard calculation, and this is the Hobart parameter, 1.89. And the red curve is the BCT structure basically is a rectangle with an atom in the center, and the blue one is an FCC, an atom in one of the faces in a cube. And thorium is FCC actually, so I get the correct result here. FCC is lower in energy than BCT. However, I am a little bit farther from the experimental point of view. This is experimental measurement, and in the minimum is my minimum value of volume, equilibrium volume. So quite far. If I include this interaction, then I get practically the experimental value for the FCC phase. So my calculation is improved. My results are improved just by inclusion of this strong correlation, electronic correlation in my calculations. But the improvement is very marginal, is very small. However, what about protactinium? Well, for protactinium, if you made the things right with all the details, putting details in the numbers and all the stuff, a standard calculation gives you the wrong answer because protactinium is ground state phase is BCT, but a TFT calculation gives you a lower energy for FCC, which is wrong. It's not representing the reality of the experiments. And I played months with this calculation, tried to see if I'm making a mistake. I'm making a mistake in getting the results. Everything was fine. So basically, my approximation was not good enough. Including this value of electronic correlation, I get the correct description of the structural phase for protactinium, and even better, I get closer to the experimental value. So this was an insight that probably the electronic correlation is a missing ingredient in the light actiness. I think that was not included in previous calculation because of the itinerant properties of the 5F electrons. What about the electronic properties? The difference between the standard calculation and strong correlation for thorium and FCC, I got an increase in the density of states at the Fermi level of 4.2%. It's very small, but remember what happened in my previous calculation of lambda for thorium. I got a very low lambda. I wanted to increase it, okay? How I could increase, remember lambda is linearly dependent of the density of states and inversely dependent of the frequencies. So I wanted to increase the density of the states at the Fermi level. And with this calculation, the electronic correlation, I got an increase. I am in the good direction to increase my value of lambda. What about protactinium? I got a very high value. I wanted to reduce it. Well, the strong correlation electronic correlation calculation gave me a lower density of states, much lower, 80% lower. So this will help me to reduce the high value of lambda that I originally got in my former calculation. So the structural properties are telling me that I'm right, and in the right direction, and also the electronic ones. What about the vibrational ones? Well, this is the phonon vibrational phonon dispersion of thorium, comparing my previous calculation with my calculation with electronic correlation and comparing with experiments. The differences are very, very marginal, but very, very important. In some regions, I get practically the same results. In another regions, I get closer to the experiments with a more robust and accurate calculation. But the differences are not so high. So how could, and I get a reduction of the frequencies that you could see in practically all the zone. So I get another important ingredient that could help me to increase my value of lambda. Lambda will increase if I reduce the frequencies, and I get a reduction of frequencies because of this interaction. But how could I measure this effect in lambda? How much was reduced the frequencies? Because here was reduced some quantity, here small, and here even smaller. So how could I quantify this reduction? Well, basically just looking at the Elliott function for my former calculation, and remember lambda is the weighted integral as a frequencies. Well, I just look at it, the range of frequencies that is more important in the calculation of lambda, that is basically from 5 MeV until 14 MeV. So I looked at this region in my phonon frequencies, and I got a range of reduction in percentage between 1.6%, that is basically this point, and 8.1%, that is basically this point. And these are the minimum and the maximum of the changes of frequencies that they get in this range of frequencies. Until now, I'm not able, that's something I will talk to you about at the end of the talk, to calculate this value for with a strong correlation interaction. Okay, so I have to have only a I can have only a feeling how strong could be affected lambda by these calculations. So I got a reduction between 1.6 and 8.1% in my vibrational properties, and that could help also to reduce lambda. I mean to increase lambda. I made the same analysis for Protactinium, and I got the opposite effect. My dispersion is yet harder. I mean, the frequencies are larger, and also that will help to reduce the value of lambda that I already get in my former calculation of 55.2. Also, I observed the range of frequencies, and I analyzed the region, the maximum and minimum in the region of this influence, that was basically between 6 and 15 MeV. The minimum change in a high symmetry point was this, is related, is 6% of increase of frequencies, and the larger increase is in this region that is close to 18%. So again, my frequencies are getting harder, and that will be affecting negatively, in a negative way, my lambda is going to reduce lambda. So everything is pointing to the right direction, actually, and it's not a linear tendency between the two elements. Thorium is getting one influence and Protactinium another. So condensing all this information in one single slide, let me show you. Here I have the increase of lambda, the increase of the density of states at Fermi level for thorium, and a decrease for Protactinium. The decrease of frequencies for thorium and the increase of frequencies for Protactinium. And these all are the previous lambda values calculated in my former analysis, my former paper. Okay, if I include these effects, this increase for thorium and this decrease in frequencies, I got this range of values for lambda if I include the electronic correlation in my calculation. So my lambda is increasing from 45.6 to 48.3 until 551.7. Basically, I am affecting these two quantities. And I didn't have time to include it in the LaTeX code, the last equation, but I put it by hand. So basically, your lambda with the electronic correlation is proportional to the original lambda times the change in your electronic properties over the change in your frequencies. This is 1 plus the change that you are experimenting here, and 1 plus or minus this omega, and this density of state, change of density of states, also 1 plus or minus the change of density of states. So it's a kind of scaling, very basic scaling, just to give us an idea how important could be these effects. So putting all this together, I mean this, I got the right direction. I try to reduce lambda, I try to increase lambda here and reduce lambda here. At least I am in the good direction. And I am almost done. So this is the plot of TC as a function of mu star for thorium. Including this analysis, I could go from this value that was far away to the region of interest, and I got closer, very, very close to the region of interest with this very basic analysis. So I was in the good direction. And what about Protactinium? This was my original calculation, very far away from the region of interest, and putting all this information together for calculating TC, I could get in the region of interest also. So these results show us that the correlation, the electronic correlation is important for the actinides, despite that the nature of the 5f electrons is itinerant. Okay, so this is the main result of my talk. This is I wanted to show you that these interactions are important for this kind of materials, for these properties, for this very delicate and very special properties to measure, to analyze, and to study. And despite that, the values of TC are very, very small. A change of a tenth of Kelvin could affect a lot and could agree more, so to speak, my results to the experimental observation in both cases. So how is the future of these ideas? Basically, to include in a self-consistent way the electronic correlations in the line width. Why in the line width? Because we already included in electronic and vibrational properties. Why in the line width? Because the line width depends on the electron phonon coupling matrix elements. This can be calculated already, and this also, but this not. And why this not? Because we have to include in the code, basically, how the electronic correlations are affected by the perturbation in the potential, and how this perturbation could affect the interaction of the electrons available for the coupling. These are current work. We are working on that, including in a self-consistent way in the calculations. And another very interesting point that we are working right now is to try to explain this long discussion about uranium, alpha uranium, the lattice dynamics. What is the discussion? Basically, the lines are the calculation, the DFT calculation, state of the art, and the dots are neutron electron scattering measurements of the Phonon frequencies. And could you see it? This branch corresponds to these dots. This second branch will correspond to these measurements. And this branch, this line, will correspond to this data. And could you see it? There is a very, very large discrepancy between the experiments and the measurements. And has been a lot of discussion in literature. What could be the reason of that? Well, we already have the answer, and it's more clear here, the discrepancy. This branch should be here. So basically, our approach is to include the strong correlation in the analysis of the vibrational properties, and you will get a proper description of the lattice dynamical properties of uranium. Why the people haven't done that before? First of all, because the models were not be available until a couple of years ago. I mean, how to calculate in a very precise and accurate way the lattice dynamical properties from first principles, including electronic correlations. And secondly, the alpha uranium structure is extremely complicated to calculate and to get a proper description of it. So we are working on that. We have very rough results that are very promising in that direction. And finally, I always include this slide in my talks. So how is the science in action from my point of view? Basically, we are the scientists, and this is nature. And depends which kind of part of the nature are you measure, explore, and study, is the story that you are telling in your papers, in your thesis, and so on and so forth. So the idea or the paradigm that you have to follow is to get in touch each other. So with the information that you already have, we could construct the nature in a more precise and accurate way. So thank you very much.
Okay, thank you very much, Omar, for your very nice talk. And now we are open for questions. Are there questions from the assistants? In the chat, I don't see. So maybe waiting for more questions. Ask you, Omar, about you have shown some phononic bands structure, but the experiments were carried out at room temperatures.
Yep.
Kelvin. And how do you compare the experiment with the normal temperature when you are studying superconductors with very low critical temperature.
No, yeah, sure. You're absolutely right. For example, here in uranium, it's 300K, and my calculation in principle are at 0K. However, in many of the materials that you could study in general, many of them, their lattice dynamical properties, at least these properties, are not so affected by temperature. They are affected, of course, but the changes are not so dramatically to explain these kind of differences. You will expect some disagreement between tenth of an MeV, and when in the cases that you could get differences in, for example, if you compare experiments at very low temperature, for example, 10K and 300K, and you are able to see differences of the order of MeV, then you have a very interesting material, because then you have to understand from where are coming these effects, because normally the differences are not so high. So probably are thermal expansion effects or negative thermal expansion effects or another high order interaction that you are not taking into account at the very beginning. So that actually that could be good news if you are able to observe that kind of differences, the strong differences. That means that there's something even more special in that material. But normally in a very perfect world, and with any kind of excitement, you will get very small differences between low temperature phases and high temperature phases.
Okay, thank you. Another question. So,
yes, I have a question. Sorry, I had some problems to unlock my my microphone. Hello, Omar.
So, hi, Frederick. How are you?
Good, and you? So I have a question more on the application. You know me, so I was interested in ampacity because you mentioned that they use MGB2.
Yeah.
So as they use MGB2, this is quite new. I mean, I remember the Russians were working on this technology. What will be the temperature of operation if you know this detail?
If you use MGB2, are you meaning?
Yeah. In the case of ampacity, do you have this data about the temperature at which this cable will be used?
I remember I was in a talk in Germany like 6 years ago. So if I recall right, the temperature that they were using was like around 40K.
Okay, so this is hydrogen, actually.
Yeah.
Okay, this is hydrogen. Okay, I see. It's interesting because usually a lot of people, they are scared of hydrogen, no? Because it can, it can explode in very particular situation, no? So I'm interested in this because it seems to be a very big project in Germany.
Yeah, they invest a lot of money.
I see. Thank you very much. That was the question I have. I have another. Say, I will allow myself another one. Especially it's I don't know if you know. I've heard that when they mention superconductivity, and during the talk, Kamerling owns, when he received the PhD, the PhD, the Nobel Prize, second PhD, the Nobel Prize now.
Yeah.
He actually didn't talk about superconductivity. He talked about supraconductivity, actually. It's what I heard. I don't know if this can be confirmed, but I think this is the same term that we use in French, supraconductivity. And my guess is that at the time they didn't have Superman. I'm just joking.
Probably. Because it was translated to English, they wanted to put his stamp.
Yeah, I don't know. I'm joking about that, but I think there was a reason, a specific reason not to call it superconductivity, and he called it supraconductivity. And I actually I don't really know why, but this is something that is interesting, that there is this this little difference in the terminology, no?
And also in the translation. I mean, we get lost in the translation because
yeah,
I get a quote in the from the English translation of the original speech, but probably in the former language that was given the speech was actually supra, and they translated in English like super.
Yeah, sure. It's what I heard. I heard it, or I read it a few years ago about that, but I don't really recall exactly why there was this subtlety here. But that was all. That's
okay.
it on my side.
Okay.
You're welcome. Bye bye.
Okay. Another final question to the speaker.
Probably was everything crystal clear.
So if not, then thank you, Omar, for your very nice presentation.
Thank you to you. Gracias a todos.
We'll continue the program with the next talk. The next talk will be given by our foreign invited speaker, Stanislav Apostolov, sorry. Stanislav, I should mention, are you there, Stanislav?
Yes, I'm here.
Okay. Stanislav, I'm very happy that he's presenting today a talk here because, in fact, we have a common academic trajectory. I mean, Stanislav obtained the bachelor and master degree in applied mathematics in the Kharkiv National University. In fact, it's the same university where I obtained my bachelor and master degrees, but in theoretical physics. Later, Stanislav obtained the PhD degree and in theoretical physics in 2010, and 9 years later, the last year in 2019, Stanislav obtained the second degree, the Doctor of Science in Theoretical Physics. I should mention that in Ukraine, there are two doctoral degrees, and Stanislav obtained the second one. And I also should mention that Stanislav now is, despite he's very young scientist, is now head of the Department of Theoretical Physics at the Institute for Radiophysics and Electronics in Ukraine, in Kharkiv, right?
Yes.
Now.
Yes.
Okay, Stanislav, your talk will be about electromagnetic waves in layered superconductors. So you can start if you wish.
So thank you very much.
Okay, we see your presentation. Yes, you can start.
Okay. So, good day to all. I bring for your attention a report on electromagnetic waves in layered superconductors. Here is our scientific team. Valery Yampolsky is our scientific leader. Myself, Zahar Maizelis, Tatiana Rakhmanova, and Dmitry Kadyrov are the main core, and Nina Kvitka is our young fellow. Also, I want to indicate our international colleagues with which we collaborate on some of the results. Nikolai Makarov, Felipe Perez Rodriguez from Mexico, and Franco Nori from Japan. So, in the report, I tell you what is layered superconductors, about a specific type of anisotropic and nonlinear Josephson plasma in them, and why they can be interesting for the scientists. Then I present a commonly accepted model that used to describe theoretically the electromagnetic field in layered superconductors. Here I highlight 3 regimes that allow analytic study. The first one is a linear regime in which the electromagnetic description can be reduced to the effective permittivity tensor. Moreover, I show that signs of the tensor components can be different in a wide frequency range. That means a hyperbolic type of isofrequency service in the wave vector space associating layered superconductors with so-called hyperbolic materials. The second regime is a weak nonlinearity. Although such a regime in general produces weak nonlinear effects, there is a special subregime when the frequency is close to the so-called Josephson plasma frequency. Under this condition, the strongly nonlinear phenomena can be predicted. And the third regime, in this regime, we study the electromagnetic waves and the DC magnetic field together. Due to nonlinearity, the DC field affects the propagation of the electromagnetic waves and therefore gives an additional control for various electromagnetic phenomena. Next part of the report will be devoted to some phenomena that have been theoretically predicted by our group. There are self-induced transparency and superposition principles for nonlinear waves, tuning the filtering properties by DC magnetic field, and anomalous dispersion of the localized modes, resulting from hyperbolic nature of the layered superconductors. The report will be finished by some recent and current studying, and of course by conclusion. So let me start with an introduction. Layered superconductors are periodic structures in which relatively thin superconducting layers are separated by thicker dielectric layers and are electrodynamically connected to each other due to Josephson effect. Therefore, such systems represent the arrays of Josephson junctions. Among examples of such structures can be indicated the cuprate high-temperature superconductors, in which the copper peroxide layers here are superconducting, while the other layer are dielectric. The pictures demonstrate crystal structures of some cuprate superconductors. It is easy to see that the periodicity of the structure is of order of nanometers. Also, it should be pointed out that layered superconductors can be produced artificially, such as niobium, aluminium oxide, niobium, or molybdenum, germanium structures. In this case, the layers is more thick, and the thickness depends on the fabrication process. It is interesting and important that the electronic plasma in layered superconducting structures supports the propagation of the electromagnetic waves. Moreover, the characteristic frequencies of so-called Josephson plasma frequency is relatively low. For example, in the cuprate high-temperature superconductors, such frequencies lay in the terahertz range that is of practical interest in physics, chemistry, astronomy, biology, medical science, and even in security and environmental control. Therefore, the layered superconductors can be the components of devices that generate, transmit, convert, and filter terahertz waves. This is an example of experimental generator. So, the layered superconductors can be interesting material for the terahertz optics. Moreover, the Josephson plasma formed in the layered superconductors is interesting for the fundamental science by itself, because it is strongly anisotropic and nonlinear. Indeed, the currents flowing along and across the superconducting layers significantly differ not only by their magnitudes, but by their nature. The alone current is the same as in bulk superconductors and can be expressed in terms of the corresponding projection of the vector potential. Here, lambda is the London penetration depth in the bulk superconductor from which the superconducting layer is made. The cross current flow due to Josephson effect and nonlinearly connected with phi, the gauge invariant phase difference of the order parameter. Here, GC is a critical current. So this strong anisotropy and nonlinearity of the layered superconductors provide interesting and unusual electromagnetic phenomena, some of which can be presented in the following report. Let me proceed with the model appropriate for the studying of electrodynamics of layered superconductors. Firstly, I present shortly the derivation of well-known coupled Synchrodon equations. We start from the specific polarization, for simplicity, when magnetic field is directed along the layers. Then the current is expressed due to the London and Josephson series. Theta L here is a phase of the order parameter in Lth layer. When we're considering only the propagation of a wave without any other external disturbance, we can take away theta from the equations. Then, the gauge invariant phase difference phi is determined only by the vector potential. Sigmas are the quasi-particle normal conductivities. They produce the dissipation of electromagnetic waves, and they should be incorporated in further investigation. However, now, also in the sake of simplicity, we assume the ideal situation and neglect them. And also we assume that layers are thin in comparison to the wavelengths. This supposition is fulfilled for the cuprate superconductors with nanometer thickness of layers and terahertz waves. Then the integral here can be simplified. So, using Maxwell equations in superconducting and dielectric layers independently, and relating magnetic and electric field to the vector potential, and excluding all the quantity except the gauge invariant phase difference phi, we get a set of differential equations, the so-called coupled Synchrodon equations. Here, lambda AB and lambda C are the effective London penetration depths across and along the layers respectively. Indexes A, B, and C corresponds to the crystallographic AB plane and C axis uniaxial crystal. Omega J is the so-called Josephson plasma frequency, and DL is the finite, in the second order, finite difference operator. Indeed, the finite difference operator, finite difference equations are not so convenient to the further analytical study. In most cases, we can assume that the layers is much thinner than the wavelengths across the layers, and we can consider the layered superconductor as homogeneous but anisotropic medium. In this medium, the currents are described by the mentioned London and Josephson theories. But I should point out that we spread evenly the lone currents spread over the medium. And a lone current, and right here, the lambda AB instead of simple lambda. Also, we relate the phase difference with a cross projection of the wave vector potential, and we can use simple yes. Therefore, we get the closed equation, plug in the currents into the wave equation, closed equation over vector potential. This wave equation is well consistent with the previous Synchrodon equation. Indeed, excluding a lone projection of the vector potential, we can get the continuous limit for the Synchrodon equation that differs from the previous slide by 2 points. The finite difference operator nature transform into the derivative, and additional derivative with respect to y is appeared. It should be noted that the wave equation is useful in the case when z component of vector potential and with it the gauge invariant phase difference are equal to 0. Then Synchrodon equation is not applicable and only the wave equation can be of use. And I point out again, these equations is nonlinear due to sine phi. Now we consider several special regimes that allow to study electromagnetic waves analytically. Firstly, we discuss the linear regime. In this regime, we can change sine phi to simplify, and then a cross current is linearly expressed via that projection of the vector potential. Then we seek a solution of wave equation in the form of monochromatic wave, frequency omega, and applying all this to the wave vector, wave equation, we can rewrite it in the form containing the effective permittivity tensor. This tensor appears to be diagonal with equal xx and yy components and different zz component. Indexes A, B, and C, as usual, corresponds to the crystallographic A, B, and C axis. Here you can see the anisotropy parameter gamma that is equal to ratio of penetration depths alone and across the layers. For most of layered superconductors, this parameter is great, of order from tens to hundreds and even near 1,000. If we take into account the quasi-particles' normal conductivities, the effective permittivity tensor gets the following dissipative terms. Parameters nu is proportional to normal conductivities. Analyzing the effective permittivity tensor, it is easy to conclude that in the wide frequency range, when frequency is between the Josephson plasma frequency and the Josephson plasma frequency multiplied by gamma, the signs of the A, B, and C tensor components are different. In this range, A, B component are negative, while C component is positive. Materials with such tensor are called hyperbolic materials because there is a frequency surface in wave vector space has a shape of hyperboloid. Hyperbolic materials are perspective for the applications because of negative refraction indexes and super and hyperlensing proposed theoretically and realized experimentally. And layer superconductors are hyperbolic materials. Moreover, they are nonlinear and provide additional perspectives for the applications. Then we discuss the nonlinear regimes that allow analytic study. As I said, the nonlinearity is caused by sine phi in Josephson current. How we can make use of it? A native analytical approach is to consider the weak nonlinearity, when sine phi can be expanded to the first nonlinear, specifically the cubic term. Although the weak nonlinearity in general means weak effects, there are special conditions when the linear terms here in equation near cancel each other, and this cubic term can play an essential role. Indeed, we seek a phase difference phi in the form of a wave and assume the frequencies to be close to some critical value, which I specify in a minute. Now we express phi cubed y phi, reducing the third power of sine and neglecting high harmonics. Then the Synchrodon equation can simplify to the following equation. Of course, this calculation is not strict, but it gives us the clue. If the frequency is close to the critical value specified here, and amplitude is small but not very small, the strong nonlinear effect can be produced even in big nonlinear regime. This I explain in details further. Now, again, we return to this question, how we can make use of nonlinearity. The nonlinearity provides the coupling between the external DC magnetic field penetrating the layered superconductor and propagating electromagnetic wave. The animation show how the external DC magnetic field penetrates the slab, particularly the plate, of layered superconductor along the layers. We suppose that in the vacuum behind the slab, the magnetic field distributed homogeneously, directed parallel to the layers and the interfaces of the slab, and the magnitude of the field is less than the first critical field. Therefore, it penetrates the slab only in the form of the exponentially decaying tails of so-called Josephson vortices. The solid line shows the real distribution of the DC field, while the dashed line indicates the imaginary Josephson vortices. which tails penetrate into the slab. The greater magnitude is, the deeper vortexes penetrates. To study the propagation of the electromagnetic wave, we present the gauge invariant phase difference as a sum of DC and wave components. Linearizing sin phi in equation over small amplitude of the electromagnetic wave, we get the term coupling the wave and the DC field. So, due to nonlinearity in layered superconductors, the DC magnetic field produce a sort of background for the propagation of the linear electromagnetic waves. That's all about the model we are using to study the electromagnetic waves in layered superconductor. And now we proceed to several phenomena that were theoretically predicted by our research group. The first two related phenomena which I will report are the self-induced transparency and superposition principles for nonlinear waves. To be specific, we consider a slab of a layered superconductor placed in a waveguide and wave of a certain polarization incident on the slab. As a result, the reflected and transmitted waves in general can have different polarization. In order to understand which this polarization can be, we firstly study the propagation of waves in the layered superconductor. The layered superconductor is a uniaxial anisotropic medium. Then, analogously to uniaxial crystals, the waves propagating in the layered superconductor can be classified in two types, ordinary and extraordinary, which polarization is related to the z-axis of anisotropy. Ordinary waves have the z component of electric field is equal to 0, and the gauge invariant phase difference is equal 0,2. Therefore, the Josephson current is absent, and such waves is always linear. Moreover, at the frequencies of order of Josephson plasma frequency, it is evanescent. The waves in which the magnetic field is perpendicular to the z-axis are called extraordinary, and they are nonlinear since at their propagation they excite a nonlinear Josephson current. Since both ordinary and extraordinary waves can be excited in the slab, the polarization of the incident, reflected, and transmitted waves can be different. Moreover, this effect is nonlinear. Now we study in more details the nonlinear extraordinary waves in a weak nonlinear regime, when sin phi can be expanded to the cubic term. We are looking for a solution in the form of the nonlinear wave with amplitude and phase depending on the coordinate x along the waveguide. In the frequencies, if the frequencies are close to the certain critical value and the amplitude of the wave is of order of square rooted frequency detuning, then the weak nonlinear term phi cubed produces the strong nonlinear contribution, and Synchrodon equation transforms into pair of differential equation for the amplitude and phase of the wave. Here sigma is a sign of the frequency detuning, plus or minus 1, and prime denotes the derivative of a normalized coordinate psi. Once these equations are solved, the electromagnetic field can be expressed in the following way. So, as we can see, weak nonlinearity at specific frequencies can lead to the strong nonlinear effects. Now, to study the reflecting and transmitted of the wave through the layered superconducting slab, we should write the boundary condition on the interfaces. And it turns out that the electromagnetic field in vacuum can be conveniently presented in the superposition of another two specific wave types, the polarization of which is related to the y-axis, which is directed firstly perpendicular to the anisotropy z-axis, and secondly along the slab boundary. Why these polarizations are interesting? Indeed, the first type is completely reflected, exciting only an evanescent ordinary wave in the slab. From a physical point of view, this is due to the fact that such a wave has an electric field component directed along the layers, and strong screening supercurrents flowing along the superconductor layers are excited. The second polarization does not have a corresponding electric field component, EY is equal to 0. So the screening currents are weak. These waves are partially reflected and partially transmitted through the slab, exciting an extraordinary nonlinear wave. But the most interesting result is that these waves of this polarization are reflected and transmitted through the slab independently, although there is nonlinearity of Josephson plasma. Now I try to show why. Let me write the boundary condition on this boundary for the Y and Z components of electromagnetic wave in vacuum and in layered superconductor. In general, these equations are quite complicated and mix all the waves to vacuum polarization with ordinary and extraordinary waves. However, due to strong anisotropy, we can neglect by some terms. Then the first equation reveals that amplitudes of incident and reflected waves are equal. So the first vacuum wave indeed completely reflects, and we can get rid of the same expression in the second equation, and it is clear that second and third equation together relates the second vacuum wave with extraordinary wave only. The last equation determines the amplitude of the ordinary wave. Thus, due to the strong anisotropy, the waves of the introduced polarization are reflected and transmitted independently, despite their nonlinearity. So we can formulate a specific analog of the superposition principles for the nonlinear waves. One should present an incident wave of any given polarization as a superposition of the waves of the two introduced special polarizations. After that, one needs to study the transmission and reflection of these waves independently of each other. As already mentioned, the wave of the first polarization is totally reflected, The wave of the second polarization is partially transmitted and partially reflected non-linearly. And finally, when one solves these two separate problems, the resulting reflected and transmitted waves can be represented as a superposition of the waves of these two polarizations. In several slides, I show how this superposition principle works in the problem with DC magnetic field. But now I say some words about the self-induced transparency for the waves of E polarization when EY equals 0. As explained in previous slides, the waves of this polarization are reflected and transmitted non-linearly, but polarization does not change. Nonlinearity means that the reflectance and transmittance depend on the amplitude of the incident wave. The plot shows such dependence for the transmittance by black line. It is clearly seen that the dependence has several branches, and the transmittance should make a sort of jumps when we continuously changing the amplitude. Such jumps is indicated by vertical arrows, red for the increasing of temperature, of amplitude, and blue for the decreasing of amplitude. Therefore, the dependence has a hysteresis character. Moreover, the phenomenon when the wave is totally transmitted, when the transmittance achieves value 1, tuning we call self-induced transparency. It can be seen that there are several points on the plot where the transmittance achieves 1. Okay, the following phenomena I will report is application of DC magnetic field in order to produce a polarization filter from the layered superconductor. We study the reflecting of a wave, particularly TM or TE polarization, that incident on a semi-infinite sample of a layered superconductor which is exposed to a DC magnetic field. As I said in the introduction, a DC magnetic field which is less than the first critical field penetrates into the sample in the form of an inhomogeneous decreasing field, in the form of a tail of such fictitious Josephson vortex. Here, phi 0 is a soliton solution of Synchrodon equation. Xi is a normalized x coordinate. H0 is a normalized magnetic field, and Xi0 is a coordinate of a center of the fictitious Josephson vortex. We use this superposition principle, which was presented earlier. For that purpose, the incident wave should be presented as a sum of waves of the two specific polarization indicated earlier. The first polarization is totally reflected, while the second interacts with a DC magnetic field. And the resulting reflected wave is again a superposition of these two waves. Only nonlinear extraordinary wave interacts with the DC magnetic field. Study it in details. We will seek the gauge invariant phase difference phi corresponding to the extraordinary wave in the following form. Linearizing in respect of small amplitude, we rewrite the Synchrodon equation as a linear differential equation with variable coefficient appearing because of the DC magnetic field. So, due to non-linearity, the DC magnetic field produces a non-uniform background for the propagation of linear electromagnetic waves. In the Tron anisotropy limit that is natural for the layered superconductors, one can neglect kz lambda AB in the denominator and find an analytical solution. Then the components of the electromagnetic field can be expressed via this solution. Then we use our findings to study transformation of polarizations. We concentrate on the frequencies lower than the cutoff frequencies when the waves in the sample could not propagate and total reflection is observed. But this total reflection is accompanied by the change of polarization. We reveal that varying the DC magnetic field and the rotation angle of plane of polarization, the total change of polarization can be achieved for given incident angle and frequency. The corresponding optimal values can be found analytically by these expressions. To illustrate this result, I present the density plot of the degree of transformation from Tm to Te reflected wave maximized by DC magnetic field. It is easily seen that for these values of rotation angle, the total transformation R equals unity occurs. So the layered superconductor appears to be a filter, strictly speaking, transformer of the polarization tunable by DC magnetic field. Now we discuss the anomalous dispersion of the electromagnetic waves localized on the layered superconducting plate. We consider a plate of a layered superconductor in a dielectric environment in which localized waves propagate across the layers. We study the waves with polarization when magnetic field directed along y-axis, that is, along the layers and along the interfaces. The electromagnetic field of localized wave is evanescent in the dielectric environment, so it can be described by such an exponent. Here Q is a longitudinal wave number and Kd is a decrement of evanescence in transverse direction along the axis. The field of localized wave can be both evanescent or oscillating across the plate of layered superconductor depending on the frequency. Moreover, it is well-known fact that in the symmetric system as our localized waves are only symmetric and antisymmetric. All the representative distributions of the field are shown on the slide, oscillating leftward, evanescent rightward, symmetric in the top, and antisymmetric at the bottom. So, electromagnetic field in the plate of layered superconductor can be expressed via cosine or sine for symmetric and antisymmetric waves respectively. Here, Ks is a transversal wave number in layered superconductor expressed via the tensor of the effective permittivity tensor. Matching the tangential components of the electromagnetic field in the dielectric and layered superconductor, we can derive the dispersion law for the localized waves. It is slightly cumbersome, so I show plot of dispersion curves as function omega of q. Let me remind you that the components of the effective permittivity tensor can take different signs in the intermediate region when normalized frequency omega is between 1 and gamma, anisotropy parameter. And namely, in this frequency region, the dispersion of the localized waves can be anomalous. The dispersion curves are decreasing with q. Moreover, the dispersion curves are non-monotonous and have the points of maxima. In these points, the group velocity of the wave can be effectively zero. Now we add a DC field in the same system. So we consider a plate of a layered superconductor exposed to a DC magnetic field. Of course, there also exists the localized waves, but the electromagnetic field is more complicated than it. This plot demonstrates that the DC field effectively supports the wave to be oscillatory. Indeed, see the main panel. Near the borders of the plate, the wave oscillates, but deeper inside the plate, where DC field is almost absent, the wave is evanescent. We study the dispersion law for such localized waves. It is revealed that the DC magnetic field shifts the dispersion curves to the lower frequencies. So the tuning of the DC magnetic field can provide a certain control of localized waves. One of interesting phenomena that can be qualitatively predicted is an internal reflection in inhomogeneous DC magnetic field. What I mean? If the plate is exposed to DC magnetic field, but inhomogeneous in the Z direction, then the localized wave change their dispersion while propagating through this inhomogeneity. And parameters can be chosen in such a way that wave reflects in some certain point. Now, before finishing, let me say some words about current studies. Firstly, we studied the excitation of the localized waves in the DC magnetic field. In particular, we show that tuning of the magnetic field is more convenient tool than tuning the frequency. This plot shows that changing the field, the DC magnetic field, by the tens of persons are equivalent to change of the frequency by fraction of persons. The other study is devoted to the response of the layered superconductor to a laser beam. This study is close to the possible experimental realization because real slabs of layered superconductor are small, millimeters or centimeters, so the waveguides and laser beams are more relevant than plane waves. In this study, we show that the focusing of the laser beam non-linearly depends on amplitude of the beam. Even the hysteresis may occur. So let me summarize. The lattice superconductors are highly anisotropic and nonlinear media. The electromagnetic excitation in it lays in terahertz frequency range, perspective in many areas of human science and technology. The lattice superconductors behave as so-called hyperbolic materials, providing negative refraction and anomalous dispersion. Specific nonlinearity and interaction between the wave and DC magnetic field make the lattice superconductors to be interesting for both theoretical study and applications. In the report, I present the conventional model that based on coupled Synchrodon equations and show how it can be possible to solve them analytically in linear and some special nonlinear regime. In addition, we discuss some phenomena that are predicted by our scientific team using the presented model and approaches. Thank you for your attention.
Thank you, Stanislav, for your very interesting talk. And now we are open to questions from the audience. Is there some question? So to begin,
maybe in chat, no?
Yes, we will wait, but for the moment, I would like to ask you, Stanislav.
Okay.
Model you use the continuous model, but local model, local continuous model. In fact, your permittivities for the components, I mean, for the description of the electric function of the layer superconductors, these components depend only on frequency, but not on, for example, on the wave vector, as in the non-local case, or also there is no dependence also on the damping effects. So could you comment why these assumptions can be done here?
Okay, really, your non-local model, of course, should be applied, but only as I know, when the frequency is close, very close to Josephson plasma frequency. As I know, we use near Josephson plasma frequency weak nonlinearity, but in our we do not need very close to Josephson frequency, and in most of polarization, when we rotate the plane of incidence, the critical frequency where non-linear regime effects should be, this frequency is not equal to Josephson plasma frequency. So as I know, in our results, we do not need use the dependence of the wave vector. But you are right, of course, if we should be close, very close to Josephson frequency, we should take into account this model, yes.
And also about the damping effects, you neglected them.
Yes, I forgot about it. Yes, damping effects we use, as you remember, I said that we now when I present shortly present a model, 1 minute, I try to find the slide. Here, when I present a model, 1 minute, here, when I derive equation, Synchrodon equation, I really neglect the normal conductivities, the damping effect, but it's only for convenience, for simplicity of calculating. But in the following slides here, now, 1 minute, here I present how these conductivities should enter to the permittivity tensor, for example, and also we can do the same and in nonlinear effects. And in our results, not presented here, we take into account the dissipation, of course, but it should be say 2 words about it. These parameters new, for example, these dimensionless parameters, they are small at sufficiently small temperatures, as we estimate for cuprate superconductors at low temperatures. These parameters is of order of 10 in -2, -3 degree. So the dissipation, of course, should be should be included, but for some effects, it's not so. It's not qualitatively change effects. I said.
Okay, maybe this answer is related with there are several questions. Maybe this answer is related with the question of Javier González Medrano, who asked that the model considers that the losses depend
on frequency. I see.
Yes.
Yes. Of course. Indeed, this dependence and they depend on frequency and depend on temperature. But as we think that they are small and neglect them, that is not need. But really, it's a very hard question. How they depend on frequency. Of course, the experimental measurements of these dependencies is very maybe not very hard, but it's hard to find in papers.
Okay.
I said so.
Okay, and there are other questions. Guillermo Alejandro Perez asked, how advanced are the experiments in these topics? So, in general, how advanced?
Okay, the experiments in yeah, I start from my report. Our results is theoretical, and unfortunately, there is no, or almost no, experimental realization of such problems. But there is one experimental result that shows that self-induced transparency is can be realized in layered superconductor. Now, what is done for the layered superconductor in more wide way? It's a lot of works on generation of experimental generation of terahertz terahertz radiation, coherent terahertz radiation, and some experiments. It's on interaction of intense laser beam with layered superconductors. So we try to shift our studies to experiment, and now you see the current study is a laser beam, and we try to find out some additional ways to experiment.
Thank you. The same person, Guillermo Alejandro Perez, asked, could these systems also be used as tunable terahertz sources?
Yes, it's as I said now. A lot of papers reports, experimental papers reports about generation of terahertz radiation. Not I know. I do not. I could not say about tunable. I think that is of course this is tunable, but in what way I do not know exactly. But yes, it's a good source of terahertz radiations. Yes.
Okay, and finally, there's another question. Pedro Valdez, in Spanish, I translate. Good talk. One question. Introducing a magnetic field, applying a magnetic field, produce maybe that the components of the permittivity tensor outside the diagonal be different from zero, yes or not?
No, the permittivity tensor keeps diagonal form, but indeed that component gets additional that component gets additional term, something like now just one a minute, something like that, something like this cosine, hyperbolic cosine, and this term depends on x, on psi.
Okay, so there is no coupling between the
yes, no coupling, no coupling on only
no.
that component depends on magnetic field.
Okay, thank you, Stanislav. Very nice talk. We thank you for your kind response and participate here for participating here in our school on superconductivity. Thank you. We will continue according to the program. And there is a small break, coffee break maybe. And we right now, according to the clock, is 12:25. So we will begin. I recommend to begin after 20 minutes, if you agree. We can begin at 12:45. The round table about the present and future of the superconductivity, mainly in Mexico, of course. So, so I will wait for you at 12. 45, okay? So there is a break now, coffee break if you wish. Bueno, ¿estás ahí, Miguel? Frederick.
Sí, aquí estamos.
Bueno, entonces a las 12:45 comenzamos, ¿sí?
Está bien,
Sí,
12:45.
Sí, y bueno, yo voy a esperar y ojalá participe la mayoría de la gente. ¿Está bien?
¿Vas a ofrecer café?
Ahorita les ofrezco café, pero debido a la situación solamente va a ser virtual. Muy bien, muy bien. Pues ya creo es la última, ¿no? La última.
Sí, la última sesión de la Escuela de Superconductividad.
Muy bien. ¿Qué tal, Frederick?
Ya, ok, estoy de vuelta. Tuve problemas de internet, se desconectó, reconectó, ya, estoy.
Se te escucha poco.
¿Qué? ¿Poco?
Se te escucha
¿Me
poco.
escuchan bien? No sé qué está pasando.
Voy a poner mi presentación, una pequeñita presentación, no es mucho, pero
Hola,
se
¿me
puede
escuchan
compartir,
mejor?
¿sí? Probar si lo puedo compartir.
No, me imagino.
Hola, Alberto. ¿Andas por allí? Beto. Alberto, ¿andas por allí? Me está mandando mensaje en clave Morse. Yo creo que es Frederick quien está mandando mensaje en clave Morse.
No te mando nada. ¿Me escuchas o no?
Sí, ahora sí.
Ok, perfecto. Ya, para ser seguro. No te estoy mandando nada.
Bueno.
Frederick, aquí para compartir la pantalla, ¿qué hay que hacer?
Tú vas en Present Now, abajo, cuando tú vas abajo donde
Presentar.
hay Present Now, tu
Sí.
clic, tú tienes que, tu clic, tú dices Your Entire Screen, tu clic, te debería dar la opción de poder presentar tu pantalla.
Toda la pantalla.
Toda la pantalla.
Tengo que apretarle. Es que se me olvidaba, hay que apretarle ahí a la pantalla.
Sí, tienes que apretar.
Sí, porque no me salía compartir, digo, pues a ver, voy a intentarlo. A ver si sale para probar, ¿eh?
Ok.
A ver, ¿logras ver lo que tengo?
Te toma algunos segundos. Ya,
Sí.
hecho. Vemos,
Bueno,
vemos la
a ver,
pantalla donde yo
déjame.
estoy hablando.
¿Ves algo?
Sí, vemos el programa.
Muy bien. Ahora esta me importa. Esta, ¿la ves?
Ya, vemos.
¿Sí?
Corta, escuela, mesa redonda, presente y futuro de la superconductividad.
Ya lo tenemos. Con eso ya.
Hecho.
Sí, entonces así es.
Te mandé a Miguel y a Carlos una carta de participación para los colegas. Está escrita.
Déjame.
Está escrita.
Okay.
Hola. Hola, Miguel.
Hola, te escucho.
Hola, Miguel. No sé, no entendí muy bien. Entonces, yo la mandé para que puedan poner su firma electrónica, ¿no? Su firma a la mano de manera numérica, para poder generar las cartas para todos los participantes, colegas, ¿no? Lo mandé por correo hace una hora, algo así. Entonces, cuando verifican sus correos, si pueden hacerme el favor de poner su firma, con eso yo genero todas las cartas para todos los participantes, colegas.
¿Me escuchas, Frederick?
Sí, sí, te escucho.
En nuestro instituto hubo un problema. Se cayó el sistema y algunos pues no podían entrar y recordaban, tenían su correo ahí en el instituto y tenían la dirección. Entonces los estoy viendo en el WhatsApp.
Ok, ok.
Entonces no sé si todavía esté funcionando, porque si me enviaste esa dirección, algo, ahorita no puedo accesarlo. Voy a checar.
Ok, entonces, si no, cuando puedes, cuando se pone de nuevo, se recompone el servidor en la web, solamente para que la próxima semana mandamos esas cartas de participación, ¿no?
Ya está, ya estoy verificando si hay acceso, fue al inicio, en la mañana.
Ok. No, yo no recibí error, que como tú no recibiste nada, entonces yo me imagino que está en el servidor.
Llegó, ¿verdad? Sí. Ahorita
Ya,
voy
yo creo que.
para verificar. Sí, ya la tengo, sí, está muy bien.
Solamente que
Bueno, nada más, terminando, pues la escuela ya te firmo.
Sí, no hay urgencia, se solamente avisa que tienen eso. A ver con Carlos si puede generar una carta, o no sé si Miguel lo hizo, generar una carta para los alumnos en español y ya, creo que con eso está bien.
Sí.
Y también para los invitados, ¿no? Yo creo.
Ya, lo que hice, lo hice en inglés para los invitados.
Sí, sería bueno para
Mandaste una carta nada más, Freddy.
Sí, pero todo lo que necesito es que me